We've learned several different ways to factor. In this lesson, we're going to learn how to factor more complex polynomials given one known root or one known zero. Remember, roots and zeros are synonymous. So in this example, we want to completely factor the polynomial x cubed plus 12x squared plus 47x plus 60, given that x equals -3 is a zero of the function. So what we're going to do here is we're going to apply the factor and remainder theorem. If the zero is x equals -3, that means that x plus 3 must be a factor. So what I'm going to do is I'm going to divide out the x plus 3 and factor whatever's left over. That way I can completely factor this polynomial. So I'm going to set this thing up for synthetic division. I have 1x cubed plus 12x squared plus 47x plus 60. And in the box, remember my factor is x plus 3, but the 0 is what goes in the box. So the x equals -3 is what goes in our box. And we're going to go through and complete our synthetic division process. So we drop the 1, and then we multiply. -3 times 1 is -3. And then add 12 plus -3 is 9, and repeat. -3 times 9 is -27. 47 plus -27 is 20, and multiply. -3 times 20 is -60, and 60 plus -60 is 0. Now, duh, of course, we have to get a 0 here because it literally told us in the problem that x equals -3 is a 0 of the function. So when I plug in -3, I have to end up with a remainder of 0. So I should know that that's going to happen before I even start the process. Now, what we want to look at from here is what's left over after we did our synthetic division. So if my remainder is 0, I have a 20 for my constant, the 9 gets an x, and the 1 gets an x squared. So I'm working with x squared plus 9x plus 20. And the whole purpose is to factor this problem. So I'm going to take that and I'm going to factor. 3 terms, so I want to know what multiplies to 20 and adds up to 9. That would be x plus 4 and x plus 5. 4 times 5 is 20, and 4 plus 5 is 9. Now remember, we want the complete factorization. So I have these two factors in green, but I also have that original factor that they told me about in the beginning of the problem. Since x equals -3 was a 0, that tells me that x plus 3 is a factor. So this would be my final factorization of our polynomial. All right, let's try one more of those. Here we want to completely factor x cubed minus 2x squared minus 9x plus 18, given that x equals 2 is a 0 of the function. So right away, if they tell me that x equals 2 is a 0, then I know that x minus 2 is a factor. If I apply the factor and remainder theorem, all I need to do is divide x minus 2 out of my polynomial, and then I'll be able to factor whatever's left over. So here we're going to set up some synthetic division. I've got 1x cubed minus 2x squared minus 9x plus 18. And then in the box, remember, you're always writing what x equals in the box. So this is x equals 2. And we drop the leading coefficient, and then we're going to multiply. 2 times 1 is 2, and add. -2 plus 2 is 0, and repeat. 2 times 0 is 0, and -9 plus 0 is -9, and repeat. 2 times -9 is -18, and 18 plus -18 is 0. That last number is your remainder, and again, duh, this has to be equal to 0 because they told me that in the original problem. They said that x equals 2 is a 0 of the function. So when I plug in x equals 2, it makes sense that it equals 0. Now, what I need to do is factor. So I'm looking at what's left over here. The remainder was 0. The negative 9 is our constant. So that means this gets an x, and here we have x squared. So really what I'm looking at is x squared minus 9. And I recognize something special here. I am working with the difference of two perfect squares. So the square root of 9 is 3, so that leaves me with x plus 3 and x minus 3 for my factors. Now, don't forget about the original factor from the very beginning. When they told us that x equals 2, then I understood automatically that x minus 2 was also going to be one of my factors. So here we have three factors, x minus 2 times x plus 3 times x minus 3.